On this one, a local engineering firm had to conduct a series of layoffs. The company has 180 employees that could be laid off, and they'll choose 10. All of them are equally qualified, so the company decides to use a lottery system to carried out by the manager to decide who gets laid off. Well, the manager posts a list of the employees. 5 of them are women, 5 are men. One of the women claims that this is gender discrimination and starts a lawsuit against the company. Well, the manager says, how can there be gender discrimination when half the employees were male, half were female? What other information do we need to understand her claim? Exactly. We need to know what proportion of the employees were female, right? We don't know that, so we don't have all the information, but here's what I can tell you. There's 60 females at this company, and there's 120 males. Do you see why she might think it might be discrimination at this point? Now it makes sense, right? Okay, so we're going to run a simulation choosing 10 employees at a time and see what percent come out female. See if this happens, if we really do get 50%. All right? So then it says, how can we use the simulation using a random number generator, it's our calculators, to investigate this? Well, detailing out a process. So let's think about this. Yeah, you don't want to use those too hard. Those are weird. I know, right? All right, so do you see that this is like 1/3 female and 2/3 male? Does that make sense, everybody? So what I would do, there's more than one way you can do this correctly, so this is just one way. I would assign number 1 would equal a female. Number 2 or 3 would equal a male. And then I'm going to use a random number generator to select 10 numbers. Can we use repeats?
Well, yeah.
Yeah, we can, right? It's just male or female. It's not individuals, right? So repeats, okay. And then ultimately, what am I going to do with those results? I'm looking for find the percent of female in each sample. So in our calculators, you don't have to remember these steps, but we're going to go to math, over to probability, and we're going to choose number 5. Rand int. Does this ring a bell? So we're going to say, okay, choose a number between 1, you might need to put a comma, and 3, right? And a comma. And how many numbers do we want it to choose? 10. Now, all 10, before you hit enter, all 10 numbers aren't going to fit on your screen. It's going to scroll off to the right. So, but don't hit down. When you hit enter, scroll to the right and count how many 1s you got, right? We need to know how many 1s, and that's your percentage of females. 1, 3, 10. So like my first sample, I got 0. So, oopsies. So I got 0. So now we're back to the same question. What percentage of the dots represent half or more females getting laid off? All right, so here's half, right? I don't even know how many dots we got. How many did we got? 14, 15, 16, 17. So there's 17 out of 19, 21. Oh, how about that? Exactly 50. So that's a 34%. Yeah? Okay. So 34%, or half or more females being laid off. All right. So now we're back to what we just did in the previous simulation. Interpret this percentage in context. So what's the assumption we're making about the lottery? It's what? Say it again?
It's truly random.
It's truly random. It's fair, right? It's fair. Okay, so we're going to say, assuming the layoff lottery is fair. You can say truly random. That's fine. Assuming the layoff lottery is fair, there is a 34% chance of getting okay, what was the proportion of females in that sample that she's questioning? A p-hat of 50% or more purely by chance alone. You can say chance alone or by random chance alone, something to that effect. Assuming the layoff lottery is fair, there's 34% chance of getting a sample of 50% or more purely by random chance. Are we okay? Logically, we're good? Okay. So then do we have convincing evidence that there's discrimination here? No. Why? 34% is greater than 5% last I checked, right? That's where it becomes suspect. So we would say, let me say it this way. Since 34% is greater than 5%, we do not have convincing evidence that the lottery is unfair. We don't have evidence for that, okay? Now, we haven't actually written a null yet or an alternative, but we're about to. It's not hard, okay? You've done it logically, you just got to throw a symbol at it. You ready for the next page? Cranking. Look at this. Okay. It's okay. It's really not that bad. Okay? So, hypothesis. The null hypothesis. So, there's that H-naught thing again, right? When we draw a hypothesis or write a hypothesis, it's always about the population, so we use parameter symbols. It's either going to be P for proportion, no hat, or mu for means. You got to choose the right one. Again, it's all about reading your question and knowing which one it is. And it's always going to be equals, and then some number, and that number is the null value. It'll be stated in the question. Now, notice that the number's the same. Okay? Now, the alternative symbols are going to stay the same. Numbers are going to stay the same. What changes in the alternative, it's no longer equal. It's either greater than, less than, or not equal to. Was she exaggerating? Well, that would mean it would be less than, right? Let's see. Okay. And then over here on the right, we have the interpretation stuff we've done. Assuming the null is true, okay, HO, the null is true, there is a p-value, whatever the p-value is, probability of getting an observed result. So this is either, when you say observed result, this is where you're going to use either p hat or x bar, or more extreme, so greater than or less than, purely by random chance. And then the conclusion. We just did this. Because the p-value is less than alpha, alpha's that 5% thing. If it's less than, we do, or we have, sorry. If it's less than, we have convincing evidence. Oh, sorry, not have. So if it's less than, we do have. All right, now, I was looking at the next line down here, and that was confusing me. All right, so what if it's not, right? What if it's greater than? So if it's less than, we have convincing evidence. I can't spell. And we reject the null. So we say we reject the null. That's the language we use. If it's greater than alpha, we don't say we accept the null. Even if you were taught that in AP Bio, no, we don't ever accept the null. We fail to reject. No convincing of it. All right, we do not have convincing evidence. And what is it evidence of? The alternative. All right, it's a lot to throw at you one day. You're getting it. We okay? You've got this. All right, let's try this out, okay? Let's try it out. Factinate.com claims that 84% of teenagers think highly of their mother. To investigate this, the school psychologist selects a random sample of 150 teenagers, finds that 135 of them think highly of their mom. Do these data provide convincing evidence that the true proportion of teens who think highly of their mother is greater than 0.84? All right, so it says state the appropriate hypothesis for performing a test. Be sure to define the parameter. Guess what? This is the state step we're going to be using this chapter. All right, so in the state step, we write out our hypotheses. Now, as you look at this question, you might want to start like circling, highlighting, whatever. Is this a proportions question or a means question? How do you know? It says true proportion. There's a lot of clues in here, right? True proportion, and it tells you the claim is 84%. All right, so I know I'm going to use the symbol P. And the claim is 84%. All right, what goes in the null always? Equals, 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 equals. And then reading the question, is it going to be a greater than or a less than in the alternative? Greater, because they're saying, do we have evidence that it's greater? All right, now, there it is. Now, the only other thing we need to do is define what does P represent in this question. It's the percent of teens who think highly of their mother. So far, so good? Okay. If we don't finish all this, that's okay. We made a lot of progress today. The school psychologist performed the test and got a p-value of 0.0225. Explain what it would mean for the null hypothesis to be true in this setting. For this to be true, it would mean that truly 84% of teens think highly of their mother. And then how did we get a sample? Well, let's think about the sample for a second. The sample they took was 150 students. 135 of them said they think highly, which translates to 0.9. So that's pretty high compared to what they claimed, isn't it? So for this to be true, 84% of teens actually think highly of their mother. And the 90% sample was by random chance alone. That's what it would mean for that to be true. Interpreting the p-value, we start with the null. What does the null mean in words? Okay, assuming the proportion of teens who think highly of their mother is 0.84. So there's the null. Now we throw in the p-value. There is a 0.025 chance of getting what? Yeah, of getting a p-hat of 0.9 or higher or lower? Higher, right? We use the greater than. Or higher by chance alone. Good, 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 good. All right, one last sentence and we can be done. Look at us, cranking away. What conclusion then would you make with the alpha 0.05? That's that 5% landmark, okay? All right, so we start with that p-value. Since 0.0225, how does that compare to 0.05? It's less than. We reject the null. And what does that mean? It means we have convincing evidence that, and then I describe the alternative hypothesis here. We have convincing evidence that the proportion of teens who think highly of their moms or mothers is greater than 0.84. So notice I'm talking about the alternative in here. All right, thanks for hanging in there.